right, everyone, we are going to go through our exam 1, question 1, statics problem solution. Person 1 has a mass of 100 kilograms. So we have a mass 1, which is this. We have the mass of the seesaw, which is, so there's a mass of the seesaw, which is this. And person 3 has a mass of 150 kilograms. So we need to draw the free body diagram for the seesaw, reaction force at the pin, which is right here, and the mass of person, typo. So not the mass of person 1, mass of person 2. So I'll make sure to make that change. Actually, we'll just leave. I mean, it's a typo, but we'll get it, and we'll get it ready to go. So let's go ahead and first step, coordinate system. Be sure to indicate it. X, Y, positive directions of X and Y respectively. Remember, counterclockwise, that's going to be our positive moment. 2, what are our assumptions? We have to include the mass of the seesaw in this problem. And we're looking at the forces on the body, which is the seesaw. We're going to ignore, some of the details about the pin reaction forces. So we're just going to kind of see that here. So let's go ahead. Third step, FBD, indicate it. Free body diagram, free the body. So we have here from the surroundings, we are going to have some weight 1, where weight 1 will be equal to the mass of person 1 times gravity. Weight 2 will be mass of person 2 times gravity. Weight 3 will be mass of person 3 times gravity. And weight of the seesaw will be equal to mass of the seesaw times gravity. So we have weight here. We have a weight from person 3. We have at the very center of the, basically, and what's the total distance here? Well, at the center, basically a halfway point between the beam, we're going to have essentially the weight of our seesaw, or here. We are going to have some reaction force, or I'm going to call this normal 1 here. And then there's finally going to be, right here, the weight to person 2. Excellent. What do we do now? Sum of the forces, we can go ahead and set them equal to 0. So sum of the forces in the x equals 0. There's no force in the x. Sum of the forces in y will be equal to normal 1 minus weight s minus weight of 2 minus weight 3 minus weight 1. So we have 2 unknowns in this problem because we don't know the mass of person 2. So we don't know this. We don't know this. So we need 2 equations. So I'm going to do sum of the moment. And I'm going to be strategic. I'm going to choose the moment here because I want to eliminate that force. So if we choose to do the origin here, sum of the moment's supposed to be equal to 0. This, I'm going to have to curl, so it's going to be minus n1 because it's going in the opposite direction from our moment. Minus n1 times, what's the distance? 0.5 meters. Then the next force will actually be positive, so that is plus ws times, what's the distance? The total distance here is what? Basically, I'm just going to do 0.5. Actually, no, excuse me, because we need to actually figure out that distance. So let's go ahead and do that right now. Again, I don't like to do math necessarily. So let's do total. What are my distances here? So I have 0.75, then I have 2, then I have 4, then I have 0.5. So the total length, I'm going to call this L, big L. The total length is this, so L divided by 2 will occur at 3.625, so some of that distance there. So the distance between our point, and actually, well, because it's the end, so it actually will be this distance, so 3.625. So that's where, again, it's the perpendicular distance from the line of action of each of these forces, so that is going to be 3.625 meters. Excellent. We're also going to have a plus n3, or plus weight 3, excuse me. Weight 3, and that distance is going to be 4 plus 0.5, so 4.5 meters, again, from our distance here. And then finally, the full length of the beam, that's going to also be a plus weight 1 times the full length of the beam here. So let's go ahead. Let's solve. So I'm going to use this. I'm going to define. Actually, let's make some definitions first because we have kind of said that before. So mass 1 is equal to, I think it's equal to 100 kilograms. Good. All right, let's go ahead. Mass 1 is equal to 100 kilograms. Mass the seesaw is equal to 35. Mass 3 is equal to 150. Gravity equals 9.8. W1 is going to be M1 times G. W2 is equal to M2 times G. W3 is equal to M3 times G. And then finally, MS times, WS will be equal to mass of the seesaw times G. There we go. All right. So, and I'll keep that L over 2. Let's go ahead now and write out our expressions. So, our expressions are our equations that we need to solve for. Will be as follows. So, Fy is going to be equal to 0, which is going to be equal to N1 minus WS times W2, WS minus W2 minus W3 minus W1. So that's our equation. We have two unknowns there. Makes sense. Good. Now we have M naught is equal to 0, which is set equal to minus N times 0.5 and 1. Oops. Minus N1 times 0.5. And then I believe it is going to be plus. Yep. Plus WS times L over 2. Then it's going to be plus W3 times 4.5 plus W1 times the full length of RB. And now we're going to solve Fy, M naught, solve those two equations simultaneously. And those are our forces in newtons. Be sure to indicate that. Or actually, excuse me, N1 is in newtons. The mass of our beam is going to be this mass. Or the mass of person 2, excuse me. Mass of person 2 will be this. There we go. We got it. So that's pretty much all we have for this problem. Excellent. Now, let's go to our extra credit problem. We have a 15 meter long beam. It is a mass of, the beam has a mass of this, surface with coefficient of friction like so. So, what are we going to do? Coefficient of friction here. Well, we're going to do our coordinate system, x, y. We're going to do it counterclockwise. We're going to set that equal to be positive. Now, this is a little bit of a difficult. So we need to look at the normal force that's acting on the beam from the surface and what is our F1. So let's go ahead. Any other assumptions? We're going to need to account for friction because it's on a frictional surface. So FBD, free the body from the diagram, or free the body from the surroundings. So we have a force here that's inclined at this angle of 20, and it's 100 newtons. We also have basically this other inclined force, 157 newtons. We have another F1 acting on the beam, but we also are going to have, and actually we can't neglect the mass as either. So we're also going to have at the center, so at 7.5 meter distance, we're going to have a weight of our beam. The weight of the beam is equal to the mass of the beam times gravity. There's also going to be a normal force here as well, N1. Additionally, we're going to have a frictional force. Now, it's kind of difficult to see, or, where that frictional force will point. So I'm just going to say, again, it has to be tangential to the surface. So it either has to go this direction or this direction. I would say that 157 newtons, maybe that's going to kind of push it and slide it in this direction. So maybe it's going to pose my mu(s) times my normal 1 right here. But again, we'll see if that direction is correct or not, and we'll figure that out. Excellent. So let's go ahead and let's calculate our values. So we're going to go quit the kernel. Oh, and actually, before we do that, so let's go ahead and write out our equations. So we need sum of the forces in the x direction must be equal to 0. Now, we have this inclined angle here. So we need to kind of calculate what is the x component and what is the y component. So the x component of this force, we need to resolve that. So let's actually resolve it right now. So this component will be pushing in this direction, the positive x, and that will be what? It will be 100 times cosine of 20 degrees. Make sure you're on degree mode in your calculator. That's really, really, really important. So remember, because this is our 20, so cosine adjacent over hypotenuse, we got it. What about this y component? That's going to be minus 100 newtons because it's pointing down times sine of whatever our theta is here, 20 degrees. What about here? Same kind of idea. So we're going to have an angle inclined here. So we're going to have a minus 157 times sine of the theta. And then our x component is actually going to be pointing in the negative direction here. So that's minus 157 times cosine of the theta. So let's go ahead and let's write that out. So in my x direction, I'm going to have a positive 100 cosine of 20 degrees. I'm also going to have a positive, at least I think so far, mu s n1. And I'm also going to have, and then I'm going to have a negative minus 157 times cosine of 37 degrees. Some of the forces in my y must be equal to 0. Those forces are going to be minus 100 times sine of 20 degrees. Then I will also have a minus weight, a plus n1. And then I'll also have a minus f1. And then finally, I'm also going to have a minus 157 times sine of 37 degrees. What are our unknowns in this problem? Well, I need this and I need this. So two equations. We don't even have to calculate on this one. Aren't I so nice? So let's go ahead and let's start to type out some values. So the mass of the beam is going to be equal to 25 kilograms. G is equal to 9.8. Mu s is equal to 0.3. And that's pretty much it. So let's go ahead. I should actually do my weight of the beam is equal to mass of the beam times G. Let's get that in here. And then we can write out all those other the values here. So let's go ahead. Oops, come on, move over. I'm going to zoom out a little bit so I can type. That didn't help significantly. All right, good. So I need my equation. So I'm going to say f of x is equal to 100 is equal to 0, which is double equal to 100 times cosine of 20 degree plus mu times s, mu s times n1 minus 157 times cosine of 37 degree. So we've got that there. Then we've got f of y is going to be equal to 0, which is going to be set equal to minus 100 times sine of 20 degree minus weight of the beam plus n1 minus f1 plus or minus 157 times sine of 37 degree. All right, so let's go ahead and solve. Fx, Fy, two equations, two unknowns, right? We could have actually gotten away with this one. But let's go ahead. And F1 is negative here, and N1 is going to be the value. So actually, to be in static equilibrium, we are going to have to change the direction of this force. So actually, we have to be pointing in the up direction to kind of help it out. So interesting little problem to kind of balance out here. So we actually have to flip the direction of that F1. But again, that's what we've got. And that is the end of our problem. So we will see you all next time for basically future. Actually, I'll see you all in very future classes. It was great to have you. And I'll see you in the future. Thanks. Bye.